All right, so we will just go through some basic concepts that we have studied first, and then we will go into our questions, okay, for discussion. Okay, so these are the main concepts and topics, okay, that we have sort of covered. All right, so if you notice, this module is a bit different from other modules. All right, in other modules, generally you have full-length lectures, correct, and followed by tutorials and labs separately. All right, so the full-length lectures go very in-depth into many topics or many concepts, and then we practice them in the tutorials. Here we have learning through practice to experimentation and so on. Okay, so the mode is different, so we try to cover a lot of different areas, all right, but we may not go into in depth in all of them. All right, so not to be concerned, we will have other modules where you will go in depth, all right, into many of these areas. All right, so the first step here, first thing here is energy, power, and efficiency. So we talked about power. So we say that the instantaneous power is basically given by this rate of watt over time. That means the rate at which your power is being consumed is instantaneous power. Okay, power itself is watt. Okay, instantaneous power is the rate at which it is being consumed. Okay, the next thing is efficiency. So we saw about efficiency, for example, when we did the RGB LED. All right, and then we realized that there is a lot of loss, okay, of power in the resistors itself. Okay, so just to get a particular color, you need to choose the appropriate resistors. Okay, and in those cases, the power loss through the resistor is actually wasted power. All right, because all it does is actually just limit the current. Okay, so the alternative to that is like what one of your friends shared today, which is on the efficient PWM signal. All right, so using a PWM signal, you actually vary the voltage, correct, which in turn affects the current. All right, and then we can actually get the required color that we want with higher efficiency. All right, and the other topic that you also covered was on battery. Okay, C rate of battery. And C rate of battery, basically one C rate basically means that the discharge current, all right, will completely discharge the entire battery in 1 hour. So that is the baseline. One C rate is the baseline, and then from there we will look at different ways of using this. All right, and then we talk about series and parallel connection of batteries. When you have batteries that are in series, the voltage is increased, all right, and the current capacity remains the same. Okay, so you have two batteries that are exactly the same and I connect them in series, the voltage doubles up, okay, but the current is the same because they are in series, means the same current flows through them. Okay, whereas if I have batteries in parallel, okay, parallel components have the same voltage but the currents will add up, so the capacity, okay, has doubled. Okay, so that is the difference between series and parallel connection for batteries. And we went through this entire sort of sequence in the studio, all right, where we did step by step how to calculate the different aspects of a battery and come up with the design. All right, and then we also have introduced you to fundamentals of electrical principles such as resistance. All right, so resistance is basically the opposition to the flow of current. All right, and we saw Ohm's law. All right, and we also saw power. Okay, power can be calculated VI. All right, and in case in the use of resistors, we can also use things like I square R. All right, we cannot use I square R for non-resistive elements. Okay, so for example, in our circuit where we have a resistor and a LED, all right, if I want to calculate the power across the resistor, I can use I square R or IV. But if I want to calculate the power consumed by the LED, I cannot use I square R because you don't have a resistive component as part of the LED. All right. So the way you must calculate the power for the LED is using the IV. Okay, voltage, PI or IV, voltage times current. Okay, next is on battery. All right. So when we talk about battery sources or voltage sources, there is an internal resistance. All right, and this internal resistance will cause some voltage drop. Okay, So of course, when we draw circuits, sometimes we will draw it in this aspect. Sometimes we may just draw it just like that. And then we say this is the load. Okay, and this is 5 volts, for example. Okay, so you must see the question and the context. In some cases, if we say this is 5 volts and this is the load, calculate the current, there's no other information given, then we can say that this is treated as an ideal source. All right, but if we draw it this way or we mention it's a practical source, then we need to factor in the internal resistance. All right, so sometimes the circuit may show a practical source, sometimes the circuit may show a ideal source, okay, depending on what we are trying to do. Okay, so measurement we've already done, parallel connection for voltmeter, series connection for ammeter. All right, in the lab, um, we actually have separate devices for voltage measurement, current measurement, and so on. All right, but what you are using now is the digital multimeter, correct, which has everything built in. All right, in the next week when you come to the lab, all right, if there is time, I think there should be time, I will introduce you to some of the hardware devices in the lab itself. All right, because we have oscilloscopes there, we have digital multimeters there as well. All right, so let's see how the studio goes next week. If there's time, I'll introduce you to some of those devices that we have in the lab itself, so you know how to use them. Okay, KCL, KVL are something that we have just been introduced to in this week's studio. All right, and we also talked about resistance in parallel and series. All right, so these are, I think, basic concepts that I think all of us know. We have introduced, you have seen it somewhere, correct? Definitely, before coming here. Okay, so let's go on to our tutorial questions. So the first question, calculate the total capacity of a battery given that it can provide a current of 3 ampere for 9 hours. Okay, so capacity, okay, capacity is given as the current multiplied by the time. Okay, and the time is actually the default unit in this case is hours. So we just say that this is 3 ampere multiplied by 9 hours, which will give us 27 ampere hour. All right, or you can also write it as 27000 milliampere hour. Okay, so that is basically how you define capacity. That means this is the amount of current that it can totally discharge. All right, how fast it discharges and everything depends on how you connect up the circuit and what is the C rate at which you're operating. All right, but this is the total capacity of the battery. All right, so you just current multiplied by time. All right, so it's a very straightforward calculation. Okay, so I will just go through the questions and I will discuss. Okay, if you want to ask me anything, you can always ask me or you can put in the chat. Okay, then I will stop and I will discuss what is your question. All right, so if there is no doubt, I will just carry on. All right, so this is the given slides. Okay, so usually I like to write and explain. All right, I think it's a bit more better than just flashing the slide. Okay, so this is the slide that you will get. Okay, so we will share the tutorial solutions with you all. Okay, so those solutions will come like this. With already everything typed out for you. Okay, question 2. How long would a 6000 milliampere hour battery last if it's operated at 10 C rate? Okay, so the thinking is the same as before. The baseline is always 1 C rate. If I operate a battery at 1 C rate, it means that the entire battery will be discharged in 1 hour. Correct? Now, if I operate at 10 C rate, that means what? That means I'm going to draw 10 times more current. Correct? I'm going to draw 10 times more current. I mean, the rate at which I draw current is 10 times more. That means I can only last for 10 times less. Right? So it will be 1 by 10 of the hour. All right, which means it is 0.1 of 60 minutes, which will give me 6 minutes. Okay, so you can the battery can only last for 6 minutes if I were to operate it at 10 C rate. Okay, so it's intuitive, correct? The higher the C rate, I'm drawing current at a higher rate. That means my battery is going to last for a shorter amount of time. Okay, so that is basically this question's analysis. Okay, so that is this thing here. So as you can see, we did not actually worry about this factor here. This was never considered here. This calculation is just directly looking at what is the C rate. Okay, so regardless of where, so even if I change this to 10,000 milliampere hour, it would have still been the same answer. Correct? Because if it is 10,000 milliampere hour, at means in one C rate, I would have used up 10,000 milliampere. Correct? But if I operate at 10 C, can only last for 6 minutes also. Correct? Because it is based on the time, 1/10 of the 1 hour. Okay, so regardless of the battery capacity, the C rate will determine how long the battery can last. Okay, the next one is on power and efficiency. All right, so here we have a device where the input power is 100 watt. Okay, and it has converted 4,500 joules into useful work in 1 minute. Find the power efficiency. Okay, so in this we must remember that power is basically work done, okay, which is in joules over time, which is in seconds. Okay, so this is the way in which we relate power. So in this case is 4,500 joules, okay, over 60 seconds. So that will give me 75 watt. Okay, so once you know that this is the power that has been generated at the output side, so we can calculate the efficiency, which will be output power over input power multiplied by 100%, which will be 75 over 100 times 100%, which is 75%. Okay, so that is for your question 3 here. So it's just a basic question on efficiency, which is again something similar which we calculated in our studios as well. Okay, so these are the slides. All right, so all these tutorials that are recorded, okay, the first part, which is the studio your presentations, we will keep it for the CLC to review and do the grading. The second part, which is the discussion of the questions, I will actually upload and send you all the link. Okay, so if you miss out anything or you forget anything, you can look back at the video that I upload. All right, then you can use that for your revision. Okay, so question 4. What is the discharging C rate of a battery of capacity 6,000 milliampere hour if the discharge current is 3 ampere? Okay, so the battery capacity is 6,000 milliampere hour. So 6,000 milliampere hour is basically 6 ampere hour. Correct? Now, if I were to operate this in 1C rate, that means the discharge current would be 6 ampere. That means the entire 6 ampere would be discharged from the battery in 1 hour. Correct? But now I'm saying my discharge current is 3 ampere. Correct? That means my C rate is 1 by 2. Correct? Which is 0.5 C. Okay, so if I'm operating at 0.5 C, then my discharge current would have been 3 ampere. If I operate at 1 C, my discharge current would be 6 ampere. Okay, so that is basically how you relate your C rate to your current. Okay, so that is your question 4. Okay, so question 5. So question 5 here we are talking about the a simple circuit here. So in this case, we have a voltage source of 12 volt and internal resistance of 0.15. All right, and this is the load. So in part one, your load is 10 ohm. Okay, and you're asked to find the load current and the power efficiency. Okay, so this is basically a series circuit, correct? Because current that flows out here goes through R1 and the same current goes through RL. Okay, as long as the same current flows through two different components, then those two components are considered to be in series. All right, so the current in this case, you can calculate as V by R, so 12 divided by the total resistance. So for series circuit, the resistance you add up, so 0.15 plus 10. Okay, so that will give me 1.18 ampere. All right, so in terms of efficiency, so efficiency, we know it is output power over input power. Now, what is output power? The output power is basically the power that is consumed by the load. All right, in many analysis, we may just represent the load as a resistor. Okay, but of course, in reality, your load could be a motor, could be a LED, could be anything else. All right, so in this case, we just represent the load as the resistor. So for the power consumed by the resistor, we can take it as I square R. So I can take 1.18 square multiplied by 10 ohm, okay, I square R. And the input power is basically the power as in provided by the source. That means voltage multiplied by current. That would be 12 multiplied by the current 1.18 ampere. Okay, so if you calculate all of this, you will get 98.5%. Okay, so all that calculation, I leave it to you. Okay, but you should get around 98.5% for this. Okay, so that is the efficiency in this particular configuration where the load resistor RL is 10 ohm. Okay, how about when the load resistor is 1 ohm? Okay, so let's do the same thing. So I'll get the current IL as 12 divided by 0.15 plus 1. Okay, and that will give me 10.4 ampere. So if you compare this and this, you can see there's a huge jump in the current. Previously, the current was only 1.18. Now the current has shot up to 10.4. Okay, because of the very small load resistance. All right, and now if I calculate the efficiency, okay, the current will be 10.4 square multiplied by RL, which is 1 divided by 12 multiplied by the current 10.4. Okay, and that will give me a efficiency of around 87%. Okay, and if you compare this with the earlier one, okay, what do you see? You see that the efficiency drops a lot more than 10%. Okay, 98.5 to 87. All right, and why is that so? Okay, because when the current goes up, what happened? Okay, the overall efficiency drops because of the internal resistance. Okay, so because of the internal resistance, there is a huge drop, okay, in the overall efficiency. Okay, because more power is lost due to the internal resistance. Okay, so when there is a high current, there is a huge loss of power within the internal resistance itself. Okay, so the efficiency goes down a lot. Okay, so as you can see, this is why we need to make sure that batteries have a very, very small internal resistance, so that, you know, in the event where there's a high current, you do not consume or do not have a huge drop in the efficiency. Okay, but of course, this is just a example. All right, in reality, your load will definitely have a significant amount of current draw in most cases, and your resistance will not be so low, okay, in most circuits that we build. Okay, so this is the given slide, okay, so which you will actually get. All right, so as I mentioned, okay, when there is a huge rise in the current, okay, it causes a increase in the power loss in the internal resistance of the supply. Okay, so efficiency will drop. Okay, so this next question here is on using the Kirchhoff's voltage law. All right, so here, as you can see, we are supposed to calculate VAB, the voltage across this. Now, the voltage across this A and B is the same as the voltage across this 100 ohm. Okay, because this point here is also A, this point here is also B. Okay, they're both the same. Okay, now when current flows out of the supply voltage here, it will come here, and what will happen? It will split into this branch and split into this branch. Correct, and then it will come back in again, okay, towards the supply. Now, whenever current splits, okay, whenever current splits into two branches, then you consider both these branches as being parallel. All right, that means at this point of time A to B, the effective resistance, okay, is actually 100 parallel with 150. Okay, and for two resistors in parallel, there is a shortcut formula which is 100 multiplied by 150, R1 times R2 divided by R1 plus R2. Okay, so this is the shortcut formula you can use if you only have two resistors in parallel, and that will give you 60 ohm. Correct, that means this circuit is now transformed, okay, to look like this, where you have 100 ohm here and you have 60 ohm. So this is your A and this is your B. Okay, and this is what you want to measure, VAB. Okay, so the voltage across VAB, you can use Kirchhoff's voltage law, which basically says that the rise voltage, the sum of voltage rises will be equal to the sum of voltage drops. All right, now if you remember what we discussed in the studio, in the last studio, we define positive and negative based on the current flow. Correct, so current is always going to flow from positive to negative. So when current flows in this direction, in order for the current to flow through this 100 ohm resistor, this has to be positive and this has to be negative. For current to flow through this 60 ohm resistor, this is positive, this is negative. All right, so you can look at it from a clockwise perspective or anti-clockwise perspective. All right, so you can say that the 10 volt supply is actually equals to, okay, the voltage drop across the 100 ohm resistor plus the voltage drop across the 60 ohm resistor. Right, because this is clockwise direction and this is anti-clockwise direction. All right, so all this source is the positive on top, negative below, so current is flowing this direction. All right, so in this case, this is the opposite. So if I were to draw a loop like this, you can say that this is the source and this is the drop, this is the drop. All right, so in terms of Kirchhoff's voltage law, this is what you can get. All right, and the voltage divider rule basically says that you can take the voltage across a single component, this is the resistor, divided by the total resistance multiplied by the source voltage, okay, to get the particular voltage drop that you want. Okay, so for voltage divider rule, if I want to measure the voltage across the 60 ohm resistor, I take this resistance divided by the total resistance 60 plus 100 multiplied by the supply voltage 10. Okay, and that will give me 3.75 volt. Okay, if you calculate the total resistance, which is 160, and then you use Ohm's law, and then you apply Ohm's law again over here, you will still get the same answer, 3.75 volt. Okay, so you can calculate VAB in different ways. Okay, so here I'm using the voltage divider principle here. So 3.75 volts appears here, which is the same 3.75 volt that will also appear across this resistor because they are both connected in parallel. All right, and again by voltage divider rule, you can say if this is 3.75, then this should be what? This should be 6.25. All right, because whatever is not here will be here because there are only two components. So the full 10 volts will appear across all the components here. Okay, so this is 6.25 and this AB is 3.75. Okay, so that is basically how you do this question 6 here. Okay, so let me go on to the last question. Okay, so these are this one. Okay, so in this case, we are asked to consider the circuit diagram and see which one of the following correctly applies both KVL and KCL. Okay, so let's look at all the KVL first. Okay, so as you can see, this is this direction, this is this direction, this is this direction, and this is this direction. So let me draw all the arrows. Okay. Now, if I were to look at the first loop here, so V1 negative VR1. Okay, so why is this a negative? All right. So if you were to just look at this loop here, if I were to just draw a loop here and I were to come up with the KVL equation for this loop, I look at all the arrows in one direction and all the arrows in the opposite direction. Okay, and they should all add up. So I can write the equation as V1 plus VR3 because both of them are in the same direction, right? But this VR1 and VR2 are in the opposite direction, correct? This is going clockwise. VR1 and VR2 are going anti-clockwise. So it's equals to VR1 plus VR2. Correct? So this is the equation you get for this loop. Okay? So by rewriting it, you'll get V1 plus VR3 minus VR1 minus VR2 equals to 0. Okay, and that corresponds to this one over here. Okay, now if I look at the first one, okay, the first one is wrong because this one is wrong here. Okay, so it's wrong. Okay, for C, let's look at C. For C, you can see that you have another loop here. Okay, so you can always draw clockwise or anti-clockwise. Usually, it is quite normal to draw in the direction of the, or write the equation based on the direction of the supply voltage in that particular loop. So in this case, since my supply voltage is in this direction, I can draw a loop this way. Okay, so the two sources in this direction are V2 plus VR4, and in this case VR2 is opposite, VR5 is opposite, so it goes to VR2 plus VR5. So rewriting it, V2 plus VR4 minus VR2 minus VR5 equals to 0. Okay, so if I were to look at this, this is wrong because this implies that all of them are in the same direction. Okay, everything is positive means all of them are in the same direction. So this is wrong. This one is wrong here. This one is wrong here. And here V2 plus VR4 minus VR2 minus VR5 equals. So this is also correct. Okay, so this one is correct and this one is correct in terms of the voltage loop using KVL. All right, so we have analyzed the voltage loops here. Now let's look at the current loops. Okay, the current loop. So in terms of the current current nodes. So for current, we look at the nodes. Nodes are the points where currents will enter and leave. So in this first node here, you see that IR1 is coming in, IR2 is going out, and IR4 is going out. All right, so if I look at this node here, I can write the equation as IR1 equals to IR2 plus IR4. All right, which means that IR1 minus IR2 minus IR4 equals to 0. This is true. Okay, so that is the first. So this one is correct. All right, but since this one is wrong, then this entire option A is not acceptable, correct? Because they said we need to choose one which applies both KVL and KCL. That means I need to choose one of the option where both KVL and KCL are both correct. So in this first option A, KVL is wrong, but KCL is correct. How about this one? IR1 plus IR3 equals to 0. Okay, where is IR1? IR1 is this, and IR3 is this. So if IR1 is coming this way, IR3 is supposed to go this way, correct? All right, so effectively IR1 is in this direction, IR3 is written in the opposite direction, correct? That means IR1 is the same as negative IR3, correct? Because this is IR1. Okay, this current. So the current going this direction, we call it IR1. The current going this direction, but in the same branch, it's the same branch. That means it's the same current value, but it's in the opposite direction. So it's negative IR3. All right, so rewriting it, we can say IR1 plus IR3 will be equals to 0. So this is correct. Okay, so of course, right now we already know that this B is most likely the correct answer. Okay, because both of them are correct. Okay, but let's examine the other two. So here IR4 and IR5. Okay, so IR4 plus IR5 equals to 0. So in this case, we have the same thing. IR4 is this direction. IR5 is in the other direction. Okay, so the same thing as just now, correct? So one current IR4 is equals to the negative of IR5. So IR4 plus IR5 will be equals to 0 is also correct. Okay, but since this one is wrong, so we don't accept it. The IR3 minus IR2 minus IR5. All right. So you can see here that if I look at this branch, IR3 is coming in, IR2 is coming in, IR5 is going out. Okay. So if I look at this branch, I can write it IR3 plus IR2 okay, so there's a question. Well, give me a minute. I'll explain this and I'll come to the question. IR3 plus IR2 equals to IR5. So if I were to rewrite this, it will be IR3 plus IR2. Okay, maybe I rewrite it here. IR3 plus IR2 minus IR5 will be equals to 0. So this is wrong. Okay, so the only correct option here is B. Okay, so that is basically how you analyze the KCL and KVL. Okay, now let me come to the question in the chat. Okay, so the question, okay, so questions you don't need to put privately. Okay, you can put for in general. Okay, so let me just copy the question and put it here for everybody to see. Okay, so this is the question. So it's easier for me to explain so everybody understands the context. Okay, so current is flowing from positive side of V1, correct? And it ends at the positive side of V2, either the current flow from positive negative. Okay, so in this case, we really do not know eventually which way the current is going to flow. All right. All we are doing is we are doing some assumptions by assigning currents to, we're assigning directions to current. All right. Only when we calculate, we will effectively know which way the current flows. Rightfully, yes, the current is supposed to flow in this direction, okay, for this loop, and the current is supposed to flow in this direction for this loop. All right, and then they may combine together and flow here. All right, but we do not know exactly how it's going to flow until we calculate all the values. All right, so these are just arbitrary directions that we are putting. Okay, so when we are solving a circuit, since we do not know exactly which direction the current is flowing, we can assume some directions first, and then after we solve it, then we will get the actual value. All right, so we will actually get more practice on this in the subsequent studios and tutorials. Okay, where we will look at other circuits with actual values. All right, and then we will see, all right, how do we make an assumption, and after we get the final answer, we must go back to our assumption and see whether the assumption was correct or not. All right, so as long as you understand the basic concept of how to apply KVL and KCL correctly here, okay, then you should be fine. So this is basically the sort of final solution you will get. Okay, but let me go back to my slide here so you can see all the working. Okay, so for the closed circuit of V2, isn't the current IR2 flowing from positive to negative V1? Okay, so what would happen in this circuit is there will be current that flow out of V1, current that flow out of V2, and they will both sort of merge and flow through R2. All right, and then it will split back and flow back into V1 and V2. But the exact amounts we do not know. Correct? We know that this is how we expect the circuit to behave. All right, so the current that flows out of both these supplies can eventually be combined here and then flow back into V1 and V2. All right, so we do not know exactly how much or the exact current yet. All right, so this is just looking at the analysis based on the direction. Current direction flowing through R2 is from positive to negative. Yeah, I mean, currently we are assuming the current is flowing in this direction, which is from A down to B. Okay, so that is why we're talking about this. Okay, so okay, I understand the confusion. This arrow, the arrow that I draw here is the indicating the voltage. Okay, the head of the arrow is higher voltage, the tail of the arrow is lower voltage. All right, the arrow that is drawn on the line itself is the one that is indicating current flow. Okay, so there's two different things. The arrow that we draw on the line itself, the branch, okay, is indicating the current direction. The arrow that I'm drawing here is actually the plus and minus. The plus here is higher voltage, minus here is lower voltage. All right, so it's two different things. One is voltage, one is current. Okay, so that is basically the last question for our tutorial. So as you can see, what we want to do is to make sure that you understand these basic concepts, right, in terms of KVL, KCL, and drawing these loops in terms of analysis of circuits. All right. So again, this, like I said before, the studios are going to get more intense. The circuits are going to get more complicated. All right, and it's become even more important that you do the preparation. In the past, because of everybody doing it in the lab, it was always, in a sense, easy to rely on somebody, a group who was uh, sort of more confident with the hardware, and they would do it, and then you can just get the readings and so on. All right, but now you can't do it because you're expected to do everything on your own. Okay, so it basically means that you have to make sure you're prepared. Okay, you can't rely on somebody else in your team to do the work and then you just get the results of the data. You have to do your own homework. You have to prepare, and then you need to make sure that you are ready for the studios. Okay, so one more question here. So essentially we take the other voltage source to be a resistor when analyzing one voltage source. No. So not yet. Okay, so the other voltage source is still a voltage source. All right, but we are analyzing it as two separate loops. Okay, there are there are many different ways of analyzing a circuit. All right, so in our next week's studio, we're actually going to be learning one of the theorem, which is called Thevenin's theorem. All right, uh, where we say that how do we analyze circuits with multiple voltage sources. All right, so there's a proper technique or approach to do it. All right, so we're not saying we cannot just look at a circuit and say one is charging the other or one is supplying more. We need to have a proper way of analyzing it. So there are different theorems to use it. Okay, so there's a superposition theorem, there is Thevenin's theorem, there is Norton's theorem, and so on. All right, so and of course KVL, KCL is also another way of analyzing it. Okay, so do we assume current flow direction is the one drawn in the picture? Not necessary. You can assume anything. Okay, you can assume anything. All right. So what we are trying to show you is that I can assume any direction and come up with the equations. As long as the equations tally with my original assumption, then those equations can then be used to solve the circuit. Okay, so as you can see here, what we have done here is we have said that on this part here, we are drawing a clockwise loop. Okay, and we are assigning that this current is this direction, this current is this direction, and so on. Here we have assigned an anti-clockwise loop, and then we have current in this direction, and so on. All right, so like I said, we do not know whether these assumptions are correct. Okay, we do not know, but what we must do is we must make sure that since I assume this, the equation that I derive from this assumption must be correct. Okay, so if you look at this here, part B, this is the only combination where this, there are a few different correct equations here, correct? 2 voltage equations and 3 current equations. So what we are trying to emphasize here is, if I am going to arbitrarily assign this direction as my loop and this direction as my current, I must be able to derive the correct expressions based on these assumptions. Later on, when we finally solve it, then we will know whether these are correct or not. Okay, so for KCL, we follow whichever assumption we make. Correct. So in this case, we have drawn some arrows already. So these are the assumptions we are making. If you draw arrows in a different way, for example, then you can make your own assumptions or your own equations based on how you decide to label the arrows. Okay, the current flow and so on. So these are not fixed. Okay, this is just one way of doing it. Okay, so you can decide how you want to label the voltage drops, how you want to label the current flow, and then from there you can decide how the circuit is going to be. All right, so what we want to just show you here is, if I make these assumptions like what is already given in the picture, how do I derive the correct expressions based on these assumptions? So that is the objective only. How to actually solve this with real values, we will see next week. Okay, so next week we are going to learn Thevenin's equivalent circuit. We will see exactly how to analyze a circuit that is having so many different components, 2 different voltage sources or more voltage sources. How do we do it step by step? Okay, so the analysis part we will do next week. But here, what is important is you must understand why the ones here with the tick. Okay, so I have 5 different expressions here with a tick and 3 that are wrong. So you must understand why they are right, why they are wrong. They are right or wrong because I have made these assumptions. Correct. So with these assumptions, I must be able to derive some expressions that represent these assumptions. Correct. You cannot make some assumptions on current, direction, and loops, but then your expressions are all contradictory to your assumptions. All right. So you must make sure that whatever assumption you make, the expressions you get are valid because they are matching those assumptions you have made. Okay, so that is the main idea of it. Okay, so that is basically the end of the tutorial. Okay, like I said, is a introductory tutorial just to make sure that our basic concepts are all clear. Okay, I will still be here in the chat. Okay, in the Zoom session. Okay, those of you who are fine, you have no questions to ask, you are free to log off. Okay, the rest of you, anybody has questions, you can stay back and ask me.
Hi, Mr. Ravi.
Yeah.
Last time you told me for Mac to install the Bitscope, right? We can find software like
Yeah.
Parallels and VMware, and
Yeah.
we can ask NUSIT or
Yeah.
CIT.
Yeah.
Actually, I asked both of the department, and they say there are no free download for us.
Is it?
So does that right? They don't have it.
Actually, no. I have another student in year 2 who just downloaded from the NUS portal only.
Oh,
Let me check.
really?
But anyway, I also saw that there is actually support for Mac 64-bit for the Bitscope.
Oh, okay.
Yeah.
Right.
So maybe you go back to the Bitscope website and then you check for the 64-bit support. I heard. I just saw that it's already supported.
Okay, okay. Thank you.
Okay. Okay. So let me come back to
Thank
the
you.
questions here. Why can we just assume IR1 is okay, so you can assume IR1 to be the same as okay, so in this case you are having different branches here. Okay, so you can assume okay that since you are having different branches, all right, it is always important to label them differently, all right, and then you can use those different expressions for your node analysis. Okay, so if I say this IR1, I can say, and if I want to declare IR3 in this direction, so if I were to draw this arrow, so example, I draw this arrow here, and I say this is IR3, then I can say IR3 and IR1 are the same. Okay, because they are both going in the same direction and in the same branch. Okay, so if I were to draw that the current in this branch is in this direction, then I can say that this IR3 and I can also say the IR3 and IR1 are the same. That is perfectly fine. There's nothing wrong with it. So if I were to draw IR3 in this direction, then of course the expression that I get for this node would also change. For node B, the expression would change. And that is also fine. Okay. So what I'm trying to tell you is you can make any assumption. These assumptions that we have made are random assumptions because we do not know. So you can also make your own assumption. So for example, I can say that IR4 is this direction. Okay, so for example, if I say IR4 is this direction, then I can also say the IR4 and IR5 are the same. All right, and that is perfectly fine, and that will only mean that the expression for node A will then change. Okay, so the idea is for node analysis and KVL, KCL approach, you are making some random assumptions. As long as your expressions, your equations that you derive from these assumptions are valid, are correct, then the rest of the analysis will be correct. You know, so it is just like algebraic rules, correct? You are finding an unknown, you do not know the unknown, but you follow the rules, correct, of plus, minus, multiply, divide, and so on, correct? So it's the same thing over here. Here you do not know the actual current flow yet, but you are just making some assumption. But with the assumption, you are supposed to derive some expressions for the node A, for the node B, for the loop in the left part of the circuit, the loop in the right part of the circuit. and then later on we will analyze it. Okay, so you can make any assumption you like as long as the equations are correct based on your assumptions. Okay, so that is the main idea. Yes, you can draw arrows on with any direction. Okay, but of course, if the question already is given, has given the arrows to you, correct? For example, if let's say this question comes out in your midterm or something, correct? So we have already assigned the directions for you, correct? So if you already assigned the direction for you, then you have to follow. Okay, what I'm saying is, if let's say you are not given any direction, you're just given this plain circuit asked to analyze, all right, I'll come up with some equations, then you are free to assign whatever direction you like. Okay, but if the arrows are already given to you, then you follow them. Right, so in our case, since the arrows have already been assigned to go in some particular direction, then we follow those directions and we derive the expressions based on those directions. Okay, if you are just given a plain circuit, okay, without any direction, then you are free to come up with your own directions.
Oh, Mr. Ravi, can you hear me?
Yeah.
Yeah. So basically, what I want to say is for this question 7, we will just assume the sort of the potential difference is from the negative to the positive based on what they've given us in the diagram, like the arrow pointing.
The arrow that I've drawn, is it?
Yes.
Okay, so the arrow that I've drawn, those arrows are representing the voltage drop. All right. So in our case, since the plus and minus is already given to us, all right, so we follow that for the KVL.
Oh, so if it's not given to us, then we can assume the direction of the plus and minus through the current flow. Am I right?
Yes. Okay, so in this case, it's already given, the plus or minus is given to us, so we follow that in coming up with the KVL loops. All right, but if it is not given, then we are free to assume how we want it to be.
But isn't the plus and minus based on the current flow itself? Because current is always flowing from negative to positive.
Correct. So it should sort of match the current direction and the voltage drop. They should sort of coincide. Correct. That means, for example, here, because I draw current one going in this direction. So since current is flowing in this direction, I say this plus and minus. Correct. So for IR3 is also going from left to right, so it's plus and minus. Right?
But what I don't get is for VR4, since IR2 is flowing from positive to negative. Oh yeah, sorry, it's correct.
All right. So if let's say you want to say IR4 is the opposite direction, then your VR4, your plus should come here and your minus should come here.
Oh, I understand.
So that's why I said here we have given you this plus or minus in a direction. But if you are going to come up with your own sort of assignments, then you can assign the current in whichever direction, and the voltage drop should match those directions that you have chosen.
Oh, so for this kind of questions, when we meet these sort of circuits, we can essentially just break this circuit into two closed loops.
Sorry again?
When we meet these kind of questions whereby it's a parallel, we can essentially just break the whole circuit into two closed loops, right? And solve from there.
Yeah, I mean, the whole idea of breaking it into loops is so that we use the KVL and KCL laws to come up with equations, and then we solve those equations to find the unknown.
All right, understand. Thank you.
Okay, so I will end the session here. So don't worry, we will be meeting each other next week, all right, for the face-to-face studios. All right, so during the face-to-face studios, Anyway, look, I will send out an announcement just to make sure that everybody is clear on when you're supposed to come. Like I said, look at part group A and group B. All right, I'll send an announcement on that. And then if any questions you all still have, we will discuss during the studios next week. If you still have questions about the tutorial. Okay, so thank you very much. Okay, I will see you all next week in the lab. Okay, thank you. Bye.
Professor.
Yeah.
Yeah, one last question is for the current IR1 and IR3, we can say that they're equal is because they're from the same source, right? V1.
They are equal because they are the same branch.
Yeah, same branch meaning from the same source, you mean?
I mean, regardless of what the source, even if the source, even if V1 is not there, it is considered one branch here, correct?
So essentially, it's like a circuit. It's like a series circuit.
Yes. So that's why we say they are the same.
All right, understand. Thank you.
Okay, so thank you everybody. I'll see you all next week.